So this one says the cone pictured has a uniform area mass density D. It's got a height of the cone being 24 meters. And then there's a radius of the cone 12 meters. What you want is you want to, first of all, find a function for the boundary of the object. So you get this boundary and it has a formula, that line. So that's what I would do first, is just use like a y equals mx plus b type of thing to figure out what that line is. So our slope would be given by the rise over the run, so 12 over 24 times x, and our b is of course 0 because it intersects at the origin. So that would be the start, is finding that line there. It tells you the height of the diagonal boundary off the x-axis. But then what you want to do is find a typical slice of the shape. And you definitely want to use like a washer method for this, where there are infinitely thin discs, which are all going to be cut up along the x-axis like that. And this is just a typical one. It's supposed to have a width of dx, but it also has a surface area. And whenever you're doing calc on these kinds of things, you want to think about, is the quantity we're looking at infinitely small, or does it have substantial area, for example? And so this would not be called dA but A, because it has a substantial surface area. It's not infinitely small at all, but the width of it is infinitely thin. So that's why this one's just A and this one's dx. Now that shape would also have an infinitely small volume, dv, and it would have an infinitely small mass too, which is dm. So these are all different properties that the disk would have. So our whole goal is to take the expression for center of mass here and rewrite it, because we just don't want our limits to be dm anymore. We want to change them into dx because that is the variable that we're integrating across. See, we're going from x of 0 to a x of 24, and this is what we want to be able to set our limits as. But if we set our limits as x equals 0 to x equals 24, then we can't keep that dm in there, because we want our limits to match the differential variable, is the idea. So the whole goal is to just get rid of dm and replace it with something else. So you have to build it up one step at a time, and we use just a little bit of geometry to figure out what those relationships between the differentials are. So dv, for example, could be a product of an area times a width. That would give it 3 dimensions. You know, just anytime we find a volume, it could be an area times a width. But this is an infinitely thin volume, so we would use an infinitely thin width. Alright, now that's good so far, but we have to get area in terms of x, because it's a function of x. the area of each disk will change. Like here, it's small, and then it gets bigger, and then at the end, it's really big. So we need a formula for that. So even before I find the area, like, another important thing to find would be the radius of each disk. That's changing too. And so what is the radius? Well, I notice I have this formula, y equals 12 over 24x. And so basically, the radius as a function of x will also be 12 over 24x. So now that I have that, I could go to my area formula for a circle and plug in pi times r as a function of x squared, and that can replace my area and bring the dx down. But now that I have that 12 over 24x, that's what goes in here. It's all about making all these little substitutions until you get rid of all the other variables and just get it in terms of x's. And now I have that dv in terms of x. Alright, then we want to find dm. So we have from density formula that dm is going to be the density times the volume. That just comes from definition of density being a mass over a volume. So if you just rearrange it, multiply volume to the other side, you get that mass is density times volume. But of course, it's an infinitely thin mass and an infinitely thin volume for our disk. And now all you do is take everything that you'd found here and plug that in here. So you get dm equals d times pi times 12 over 24x squared dx. And now you have everything you need in order to finally replace dm with something better, which is in terms of x. So plug it in both there and there. So let's see, we would get x equals 0 to x equals 24 times x times d times pi 12 over 24x squared dx. Divide by x equals 0 to 24, d times pi times 12 over 24x squared dx. Anything that's constant can come out front and or cancel. So you could bring the d there out front and the pi as well. You could basically make it d times pi times 12 over 24 squared and bring all that stuff out front. And you have to leave behind the x's though. Same thing here, bring out the d, bring out the pi, bring out the 12 over 24 squared. And we have x squared dx. Now all these things are going to cancel. And notice we have our integration all in terms of x. There's no other variables, so we can definitely do the integration now. Alright, so let's see, we'll have 0 to 24 x cubed dx over 0 to 24 x squared dx. Get our antiderivative, which is x to the 4th over 4. For the top, we'll go from 0 to 24. Down here, we'll get x cubed over 3 from 0 to 24. Alright, so that's going to be 24 to the 4 over 4. 24 to the 3 over 3. And if we flip that around, we'll see that the result is 3/4 of 24. And that always happens with a cone. It's going to be that the center of mass is located 3/4 of the way toward the base. For a triangle plate, for a triangular plate, it ends up being that it's 2/3 of the way toward the base. So 2/3 of the height there. Anyway, this one was 3/4 of the way toward the base. So that's gonna be 18.